Hello everyone, welcome to Turing machines class. Okay, so this is the QR code of my compiler design textbook. This will be helpful for BTech, MTech and GATE, and you can scan this QR code and buy it from PW store. Okay, the book is available on PW store, and this is the QR code of my Telegram channel. You can, if you want any discussions related to GATE, you can join the Telegram channel. This is the QR code. Okay, fine. So yesterday we were seeing Turing machines. Today also the topic is Turing machine. Mostly tomorrow we will complete everything. Okay. So yesterday I have explained you. Three concepts, right? Or three things related to recursively enumerable, and set of all languages. Recursively enumerable, and set of all languages. Right? So if a language L1 is recursive, then language L1 complement is also recursive. If a language L2 is recursively enumerable but not recursive, then L2 complement will definitely be not recursive. Or a language can be non-recursive, then its complement may be non-recursive, right? Therefore, what are the points you can understand here? If a language is recursive, its complement is recursive. If a language is recursively enumerable, then its complement may be recursive, may not be recursive. If a language, there are some languages which are not recursive, whose complement is not recursive, right? So based on this, we will see some points, right? L is recursive implies L complement is recursive. L is recursive implies L complement is recursive, right? L is recursively enumerable but not recursive. L is recursively enumerable but not recursive. It implies L is not recursively enumerable. It implies L is not recursively enumerable, right? L is not recursive. It implies L complement. Now see this. L is not recursive, then it implies L complement may be recursive or L complement may not be recursive, right? So L is not recursive. It implies L complement may or may not be recursive. L complement may or may not be recursively enumerable. May or may not be recursively enumerable. Now L is not recursive. That implies L complement is not recursive. Right? So these are the important points that you need to understand. Okay. Mohan Maheshwaram, hi. Okay. Now let us see countability. Okay. So A set S. So a set S, a set S is countable. A set S is countable if and only if S has, if and only if S has enumeration procedure. Enumeration procedure. If and only if a set has enumeration procedure. Now, what is the meaning of enumeration procedure? Enumeration procedure means it is a procedure. Enumeration procedure means it is a procedure which lists a set. It is a procedure which lists a set with a guarantee that with a guarantee that any particular element any particular element should be listed in a finite amount of time. Should be listed in a finite amount of time. Right? So what is enumeration procedure? It is a procedure. If you follow this procedure, all the members of this set should be listed, and every member of this set should be listed after a finite amount of time, right? For example, if I take natural numbers, right? Now I can get all the natural numbers starting from 1. I will start with 1, and what I will do is, in every step I will do +1. Then you give me any number, natural number, I can generate it after a finite amount of time. You give me any natural number, I can generate it after a finite amount of time. Therefore, natural numbers are infinite. We know that natural numbers are infinite, but since we have a enumeration procedure, it is countable, which means this is countably infinite. This is countably infinite. This is countably infinite. This is countably infinite, right? This is countably infinite. Right? Now, if you see set of all numbers, there are different kinds of numbers, right? If you see set of all numbers, there are different kinds of numbers. One is natural numbers n, and natural numbers is a subset of integers, right? So integers are a superset of natural numbers. Integers z integers z and rational numbers q and real numbers r and complex numbers c. And complex numbers c, right? Now all these are infinite numbers. Natural numbers are infinite, integers are infinite, rational numbers are infinite, real numbers are infinite, and complex numbers are infinite, right? All these numbers are infinite for sure. Now the question is, out of all these numbers, what are the numbers that are countable? Out of all the numbers, what are the numbers that are countable, countably infinite, and what are the numbers that are uncountably infinite? Which means which means what are the sets for which we can give enumeration procedure, and what are the sets for which we cannot give enumeration procedure, right? What are the sets for which we can give enumeration procedure, and what are the sets for which we cannot give enumeration procedure, right? So it turns out that natural numbers are countably infinite, integers are countably infinite, and rational numbers are countably infinite, right? How can you say natural numbers are countably infinite? Because I can go on adding +1 and I will get all the natural numbers. How can I say integers are countably infinite? Because I can do +1 and -1 and I can get any integer, right? But then the tricky part is, how am I saying that rational numbers are countably infinite? Beyond rational numbers, all the numbers are uncountable. Beyond rational numbers, all the numbers are uncountable. All the numbers are uncountable, right? So now the question is, how are we going to prove that rational numbers are countably infinite? If we can prove that rational numbers are countably infinite, any subset of a countably infinite set is countably infinite or finite. If we can prove that rational numbers are countably infinite, and integers are subset of rational numbers, we can say that integers are also countably infinite, and natural numbers are also subset of rational numbers, so we can say that natural numbers are also countably infinite. Rational numbers are also countably infinite, right? So so what am I saying is, numbers can be countably infinite or uncountably infinite. Natural numbers, integers, and rational numbers are countably infinite, and real numbers and complex numbers are uncountably infinite. Real numbers and complex numbers are uncountably infinite. Real numbers and complex numbers are uncountably infinite. Real numbers and complex numbers are uncountably infinite, right? Right. Now let us see how rational numbers are countably infinite. Okay. So we are going to see enumeration procedure. If we can give enumeration procedure for rational numbers, then we can say that it is countably infinite. Enumeration procedure for rational numbers. If we can give enumeration procedure for rational numbers, then we can say that rational numbers are countably infinite. Rational numbers are countably infinite. rational numbers are countably infinite. Rational numbers are, sir, how many questions can we expect from theory of computation? So you can roughly expect 8 to 12 marks from theory of computation. It varies from year to year, paper to paper, but then roughly you can expect over 8 to 12 marks, Shyam. You can expect around 8 to 12 marks in theory of computation. Okay? 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 So, what are rational numbers? Rational numbers are 1 by 1, 1 by 2, 1 by 3, 1 by 4, 1 by 5, so on, right? And then 2 by 1, 2 by 2, 2 by 3, which means P by Q form, 2 by 4, 2 by 5, so on, right? And then 3 by 1, 3 by 2, 3 by 3, 3 by 4, 3 by 5, so on. You get negative numbers as well, okay? And then 4 by 1, 4 by 2, 4 by 3, 4 by 4, 4 by 5, so on, right? Right? Okay, okay. Now, what could be the enumeration procedure? Let us say if we have taken the enumeration procedure as, I will take every number and in the denominator I will add +1. Then what happens is, you will generate all these numbers 1 by 1, 1 by 2, 1 by 3, so on, but you will never go to 2 by 1, 2 by 2, 2 by 3, right? Which means you can generate all these numbers by adding 1 to the denominator starting from 1 by 1, but you will never go to 2 by 1, 2 by 2, 2 by 3, so on, right? So in this method, you are not going to generate these numbers, right? So this method is not a right method. Right? So just adding 1 to the denominator and generating all the numbers is not a right method. Just adding 1 to the denominator and generating all the numbers is not a right method. It is not a right method. It is not a right method, right? So what could be the other method that we could propose in such a way that all the numbers are generated? So we go diagonally, which means we generate this, then 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 we generate this, so on. So if you go diagonally, then all the numbers are going to be generated after some amount of time, and this is the enumeration procedure, right? So what is enumeration procedure? Go diagonal by diagonal. If you go diagonal by diagonal, we can generate all the numbers, right? If we go diagonal by diagonal, we can generate all the numbers. If we go diagonal by diagonal, we can generate all the numbers. We can generate all the numbers, right? Therefore, we can say that rational numbers are countably infinite, right? Right? Now, if integers are a subset of rational numbers, they cannot be uncountably infinite, right? If this set is countably infinite, then this set is also countably infinite. This set is also countably infinite, right? So how can we prove this? Because A is a subset of B, right? Because one set is a subset of other set, we can prove this. Because one set is a subset of other set, we can prove this, right? We can prove this. So how can we prove this? Let's see the theory for that, okay? So if A is a subset of B, right, B is, let us say B is countably infinite. Let us say B is countably infinite. Let us say B is countably infinite, right? Then then A is countably infinite, then A is countably infinite or finite. Then A is countably infinite or finite. Just a minute. Just a minute. Okay. Right? If B is countably infinite, then A is countably infinite or finite. Right? Right? So what can you say? Every subset of a countably every subset of a countably infinite set, every subset of a countably infinite set is countably infinite or finite, is countably infinite or finite, is countably infinite or finite, right? So what can we say? So we can say that if Q is countably infinite, Z is countably infinite and N is countably infinite, right? So if Q is rational numbers, Q is countably infinite, then Z comma N, integers and natural numbers are countably infinite. We can also go ahead and say that prime numbers are countably infinite, composite numbers are countably infinite, even integers or odd integers, even integers or odd integers are all countably infinite, right? Any subset of Q, rational numbers is either countably infinite or finite, right? Right. Now let us see a proof that now I am telling you that this is countably infinite, but real numbers are uncountably infinite and complex numbers are uncountably infinite. Real numbers are countably infinite and complex numbers are uncountably infinite, right? Now how can we say that real numbers are uncountably infinite, right? So Cantor has given a proof. Cantor's diagonalization. Cantor's diagonalization to prove that real numbers are uncountably infinite. Real numbers are uncountably infinite, right? So you think about it, how we can prove it. You think about it, how you can prove it, right? You think about it, how we can prove it, right? Cantor's diagonalization to prove that real numbers are uncountably infinite, right? So I'll give you 2-3 minutes of time. You think about how we can prove that real numbers are uncountably infinite. Okay? You think about how we can prove that real numbers are uncountably infinite. Real numbers are uncountably infinite. Real numbers are uncountably infinite. Right? Think about some method where we can prove that real numbers are uncountably infinite. Hi Mohit. Hi Mohit. Now tell me a method by which we can prove that. పోతా 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 పైసలన్నీ పట్టుకుపోతావారా, పెట్టుకున్నవన్నీ నువ్వు కట్టుకపోతావారా, పోరి పోరి అంటూ దాన్ని చుట్టుకుంటావారా, చక్కపోసి పెగ్గేస్తా ఆ ఆ ఆ ఆ. ఠీకే. ఓకే. ఓకే. Tell me about this. Now how can we prove that real numbers are countably infinite? Think about it for 2-3 minutes. Think about it for 2-3 minutes. Right? Right? So let us play a game. Okay? Now the game is, you will say that real numbers are not uncountably infinite. Now let's play a game. Okay? Let's play a game. Now you say that real numbers are countably infinite. Okay? And I will say that real numbers are uncountably infinite. That is the game. Okay? You say that real numbers are countably infinite, and I will say that real numbers are uncountably infinite. Real numbers are uncountably infinite. Now you are saying that real numbers are countably infinite. Then what does that mean? There exists a enumeration procedure. Enumeration procedure is nothing but a procedure which will list down all the numbers. Okay. Now you are saying that real numbers are countably infinite, right? Now you are saying that real numbers are countably infinite. Okay. Now I'll ask you, Now that you are saying that real numbers are countably infinite, now there is a method to list down all the real numbers. Now I will ask you to use that method and list down all the real numbers and give me the list. Simple game. Okay. List down all the real numbers and give me the list. This is a simple game. Okay. Okay. This is a simple game. Cantor's diagonalization to prove that real numbers are uncountably infinite. Real numbers are uncountably infinite. Right? Now that you are saying that real numbers are countably infinite, what I am asking you is give me the entire list of real numbers by using the enumeration procedure that you are using. Okay. So I'll go step by step slowly. Okay. So what I'm saying is you are saying that real numbers are countably infinite. I am saying that real numbers are uncountably infinite. That is the game. Okay. Now, now if the real numbers are countably infinite, then there exists a enumeration procedure. Now using this enumeration procedure, you can list all the numbers, right? So what I am asking you is, now that you are saying real numbers are countably infinite, there exists a enumeration procedure, and using that enumeration procedure, you can list all the real numbers, right? Now I am asking you for that list. Give me the list of all real numbers that you have come up with. Okay. Give me the list of all real numbers that you have come up with. Okay. Simple. Okay. Simple game. Simple game. Right. Right. So let us say you have given me a list, right? And the list is like this: 0.23146798, so on, and then 0.12579869, so on, and then 0.36798124, so on, and then 0.41689213, so on, right? And then 0.52781693, so on, and then 0.78169214, so on, right? So you have given me the entire list. Let us say you have given me a list, entire list. Okay. Now you understood the game. At least can you play it now? Now what will I do? Guess what I will do? You guess what I will do. Right. So now you have said that real numbers are countably infinite and these are all the real numbers, and I have used a enumeration procedure, right? Now guess what I will do. Now guess in this game what I will do. Simple guess, right? So what I will do is, I will try to prove that these are not the only numbers. I can come up with a new number which is not there in your list, which means your enumeration procedure has failed, right? Proved by contradiction, right? Tell me how I am going to prove that. Tell me how I am going to prove that. Tell me how I am going to prove that. Right? So a simple method what I can do is, a simple method what I can do is, a simple method what I can do is, I will take the diagonal elements, right? I will take the diagonal elements like this. I will take the diagonal elements like this. In the entire list, I will take the entire diagonal, right? Now, what I will do is, I will put these diagonal elements as a number. I will put these diagonal elements as a number. 2, 2, 7, 8, 1, 2, so on, right? Now what I will do is, for every digit, I will take 9's complement. For every digit, I will take 9's complement, which means 9's complement 2 of 7 is 7, 2 of 7 is 7, 7 is 2, 8 is 1, 1 is 8, 2 is 7, so on, right? Now, this is a new number I got. Understood this? Now, I got a new number. Now, I got a new number. I got a new number which is not there in this list, because if you look at the first digit, it is differing from this number, right? If you look at second digit, it is different from this number. Therefore, it is a new number. Like that, if you look at any number, all the numbers will have one digit change here, right? Therefore, this number is not there in the list. So your method has failed, right? Once again, let us see what I have done. So the game is, I told you that real numbers are uncountably infinite, and you said that real numbers are countably infinite, which means you have a enumeration procedure. Now what I have asked is, use your enumeration procedure and give me the list of all real numbers. Then you give me the entire list, right? And you told me that only these are the numbers possible. Then I am able to come up with a new number which is not there in your list. Therefore, your list is incomplete. Therefore, your enumeration procedure is wrong. Therefore, real numbers are not countably infinite. Therefore, real numbers are uncountably infinite, right? I have proved it by contradiction. I have proved it by contradiction. This is called Cantor's diagonalization to prove that real numbers are uncountably infinite. Cantor's diagonalization to prove that real numbers are uncountably infinite. Real numbers are uncountably infinite, right? Right? Okay. Now, there are few properties that you have to understand. If I take cross product of two countable sets, then the cross product is going to be countable. If I take cross product of two uncountable sets, then the cross product is uncountable, right? Now, if you look at complex numbers, you can write complex numbers as cross product of two real numbers sets, cross product of two real number sets, right? Now, this is uncountably infinite, this is uncountably infinite, Therefore, the result is uncountably infinite. Therefore, complex numbers are uncountable. So, if you look at this diagram, now what we have shown is, we have proved that rational numbers are countably infinite, integers are countably infinite, natural numbers are countably infinite, and we have proved that real numbers are countably infinite, and complex numbers is nothing but a cross product of real numbers. Why? Because complex numbers you are going to write like a plus bi, where a and b are real numbers, which means complex complex numbers are cross product of real numbers. That is why this is uncountably infinite. That is why this is uncountably infinite, right? So we have proved for all the numbers whether they are countably infinite or uncountably infinite, right? Right? Now, if I take x comma y ordered pair such that x comma y belongs to z, right? Now what is it? This is z cross z. Z cross z means countable cross countable. Countable cross countable. So we can say that it is countable. Countable cross countable is countable, right? Right? Now, uncountable cross countable is uncountable. Uncountable cross countable is uncountable, right? Countable union countable is countable. Even if you take union of infinite countable sets, even if you take union of infinite countable sets, the result is countable. The result is countable, right? Now, if you take union of, now if you take union of, now if you take union of uncountable union uncountable, uncountable union uncountable, you are going to get uncountable. Now, if you take union of uncountable union countable, you are going to get uncountable. Uncountable union countable, you are going to get uncountable. You are going to get uncountable. Right? Right? Let us see one other way of proving that. Let us see one other way of proving that rational numbers are countable, right? Let us see one other way of proving that rational numbers are countable. Other way of proving that rational numbers are countable. Other way of proving that rational numbers are countable, right? Now I have given you entire theorem, entire all the knowledge that is required. Now can you prove that rational numbers are countable? Can you prove that rational numbers are countable? Can you prove that rational numbers are countable? Now I have just given you the entire thing required, the entire knowledge required. Can you prove that rational numbers are countable? Right? I will give you a method. Okay. So let us say rational numbers are like this: 1 by 1, 1 by 2, 1 by 3, 1 by 4, so on, and 2 by 1, 2 by 2, 2 by 3, 2 by 4, so on, and 3 by 1, 3 by 2, 3 by 3, 3 by 4, so on, and 4 by 1, 4 by 2, 4 by 3, 4 by 4, so on, right? Now, this entire thing is countable. This entire thing is countable, and this entire thing is countable, and this entire thing is countable. Why? Because in the denominator I can keep on adding 1, that is the enumeration method. So using I have a enumeration method, so this entire thing will be countable, this entire thing will be countable, and all this countable, right? So there are infinite number of countable sets, infinite number of countable sets, infinite number of countable sets, right? Countable union, countable union, countable union, countable, so on, right? Now we know that infinite number of countable sets is countable. Therefore, this is one more proof that rational numbers are countable. This is one more proof that rational numbers are countable. One more proof that rational numbers are countable. Okay, okay. Now let us see Cantor's theorem. Let us see Cantor's theorem. Let us see Cantor's theorem, right? Right. Now let us see Cantor's theorem, right? So S is countably infinite implies 2 power S is uncountably infinite. If any set is countably infinite, then the power set is uncountably infinite. If any set is countably infinite, then the power set is uncountably infinite. Then the power set is uncountably infinite, right? And we know that natural numbers is countably infinite. Therefore, 2 power natural numbers is uncountably infinite. 2 power natural numbers is uncountably infinite, right? And integers is countably infinite. That implies 2 power integers is uncountably infinite. And rational numbers are countably infinite. That implies 2 power q is uncountably infinite. 2 power q is uncountably infinite, right? Now we know that rational numbers union irrational numbers is equal to real numbers. Rational numbers union irrational numbers is equal to real numbers, right? Now we know that rational numbers are countably infinite and real numbers are uncountably infinite, right? Therefore, what will be irrational numbers? Countably infinite set, if it has to become uncountably infinite, then definitely other set has to be uncountably infinite. Therefore, irrational numbers are uncountably infinite, right? Similarly, you can say that non-integers are uncountably infinite. Similarly, you can say that non-rational numbers are uncountably infinite. Non-rational numbers are uncountably infinite, right? Right? Okay, fine. So that is all about the countability. So in tomorrow's class, we will see rest of the topic. So tomorrow will be the last class. Okay, for TOC, we have finally approached the end. Okay, thank you so much. Good night and Jai Hind.